silicon controlled rectifier, that is SCR. The silicon controlled rectifier is a thyristor having three terminals, four layers PN and three junction device. So figure A shows the structure of silicon controlled rectifier. It has four layers PN, three terminals, gate, anode and cathode, denoted by G, A and K respectively, and three junctions denoted by J1, J2 and J3. Figure B shows the symbol of silicon controlled rectifier. The thyristor has three basic mode of operation. First, forward blocking mode. Second, forward conduction mode. And third, reverse blocking mode. So, we can study the characteristic of silicon controlled rectifier in these three modes, that is forward blocking mode, forward conduction mode and reverse blocking mode. So in order to plot the characteristic, the connection of silicon controlled rectifier is as shown in figure A, and in figure B we get the VI characteristics of SCR. So we'll study the characteristics of SCR in these three modes, that is forward blocking mode, reverse conduction mode and reverse blocking mode. First, forward blocking. When anode voltage is made positive with respect to cathode, the junction J1 and J3 are forward bias and junction J2 is reverse bias. So when we apply a voltage between anode and cathode, that is anode is positive with respect to cathode, then junction J1 and J3 will be forward bias and junction J2 will be reverse bias. Due to this reverse bias junction J2, small leakage current flows from anode to cathode, which is then said to be forward blocking state or off state, and leakage current is called as forward leakage current or off state current. Since from these three junctions, junction J2 is reverse bias, due to reverse biasing, leakage current flows from anode to cathode, and due to this, the junctions J2, it blocks a current flowing from anode to cathode. Thus, this current is called as forward leakage current or offset current. Second, forward conduction. When anode voltage is positive with respect to cathode, if anode to cathode voltage, that is VAK, is increased to a sufficient large value at zero point 0.1 shown in VI characteristic, then the junction J2, which was reverse bias earlier, will break down. This is called as avalanche breakdown, and the voltage at which this breakdown of junction J2 occurs is called forward breakover voltage, denoted by VBO. Thus, junction J1 and J3, which were already in forward bias earlier. Hence, breakdown of junction J2 results in free movement of carrier across all the three junctions that results in large forward current that is shown by point 2 in VI characteristics. But in order to limit this large forward current, it is limited by external resistance RL shown in the circuit diagram in figure A. The thyristor is then said to be in conducting state or on state. With breakdown of junction J2, thyristor can be made on by applying positive voltage to gate with respect to cathode. Thus, due to this, gate cathode junction J3 is forward bias and therefore conducts, that is, gate current flows. The forward voltage at which thyristor is turned on depends upon the gate current. More the gate current, lower will be the required forward voltage to turn on the thyristor. So, as we increase the current flowing through the gate, that is, if the gate terminal is made positive with respect to cathode, the gate will attract more number of electrons. Now, if it attracts the more number of electrons, the current flowing through gate will increase, and as the current gate increases, it will reduce the forward voltage to which the thyristor will turn on. Now, we have two currents in this forward conduction mode. First one is latching current and second one is holding current. So we'll study what is meant by latching current. It is denoted by IL. It is minimum anode current required to maintain thyristor in on state immediately after thyristor has been turned on and gate signal has been removed. So the gate signal is just applied to turn on the thyristor or to conduct the thyristor in forward mode. Thus, as soon as the thyristor is turned on, the gate signal is being removed, and once the gate signal is being removed, the thyristor will be made to is made to conduct in forward mode by maintaining the current, and this current is maintained with help of latching, and that current is nothing but called a latching current. After turn on, if anode current is more than the latching current, the thyristor continues to conduct because due to free movement of sufficient carrier, there is no depletion layer at junction J2. Since J1 and J3 are already in forward bias mode, J2 which was earlier in reverse bias mode, now if we increase the voltage at which the junction J2 breaks down, and as soon as the junction J2 breaks down, large number of carriers flows from all the four layers, that is P N, and thus due to this more current, the thyristors starts to conduct in forward bias mode. The thyristor behaves like a conducting diode, and there is no control over the conduction of device since the thyristor is made to conduct in latching mode. However, if forward anode current is reduced by some means below a level called as holding current denoted by IH, a depletion layer will be developed around a junction J2 due to reduced number of carriers, and thyristor will go into blocking state. That is, when we break down a junction J2, large number of carriers will flow through all the three junctions, and if the large number of carriers starts flowing, the current from anode to cathode will be very high and large current will be flowing from the output terminals. That is due to a latching. If we have to control this current or a large current, we need to develop a layer into a junction J2. Then and then only we can control the current flowing from anode to cathode. Thus, this can be developed with help of holding current. Okay, so now we'll study what is meant by holding current. Holding current is denoted by IH. It is minimum anode current required to maintain the thyristor in on state. Normally, thyristor is not turned on by increasing the forward voltage VAK beyond the breakover voltage VBO, because such turn on by the breakdown of junction J2 could be destructive and may damage the device. So, practically, the forward voltage is always maintained below breakover voltage, that is VBO, and thyristor is turned on by applying positive gate with respect to cathode. Third, reverse blocking mode. When supply terminals are reversed so that cathode voltage is positive with respect to anode. In forward mode, anode was positive with respect to cathode, whereas in reverse blocking mode, cathode is positive with respect to anode. The junction J2 will be forward bias, but the junction J1 and J3 will be reverse bias. In forward blocking mode, junction J1 and J3 were forward bias, whereas junction J2 was reverse bias. But in reverse blocking mode, J2 will be forward bias, but junction J1 and J3 will be reverse bias. In this case, it is like a two reverse bias diode connected in series. Due to reverse bias junctions, only reverse leakage current, known as reverse current denoted by IR, would flow through the device, and thyristor is said to be in reverse blocking state. So, if the reverse voltage, that is minus VAK, is increased to a sufficient large value, then there will be a breakdown in junction J1 and J3 which were reverse bias, and the device will start to conduct as soon as the junction J1 and J3 will break down. If junction J1 and J3 will break down, so junction J1, J2 and J3 will be forward bias and large current will start flowing through the anode to cathode. So just by controlling the voltage level, we can control the reverse biasing and forward biasing of the junction, and by controlling the reverse biasing and forward biasing of the junction, the current flowing from anode to cathode and from cathode to anode can be controlled, and thus the gate plays an important role for attracting the electrons, large number of electrons, and by putting a depletion layer between the junction.